Hello everyone, so this is example 1.1 from Hubert, the electric machines textbook. And this video is sort of a response to a question that was asked about how to solve this question. So let's take a look. So it says here, determine the voltage that must be applied to the magnetizing coil in figure 1.6a in order to produce a flux density of 0.2 Tesla in the air gap. So that's right here in the air gap. They mention here flux fringing, which always occurs along the sides of an air gap as shown in this figure. I didn't put part B, but basically I have a copy, a scan of it. Maybe I can show you. So they're talking here about the flux fringing here that would be happening here at the air gap. Okay, they're basically saying to neglect the flux fringing. Okay, I'll explain what that means in just a moment. So let's go back. So they're saying flux fringing, which always occurs along the sides of an air gap as shown in figure 1.6b, will be assumed negligible. So we can neglect the flux fringing. Assume the magnetizing curve for the core material, which is homogeneous, is that given in figure 1.5. So figure 1.5 is this one over here. This is basically, we have two curves here. We have a magnetization curve, and then we have the curve that shows the relative permeability. We're going to mainly be using the magnetization curve. The coil has 80 turns and a resistance of 0.05 ohms, and they say the cross-section of the core material is 0.04 meters squared. So this is why they mentioned that we can neglect flux fringing, because we want to basically assume that the cross-section of the core is going to be the same everywhere, even in the air gap. Now, this is of course assuming that we're neglecting flux fringing. If you're not neglecting flux fringing, then as you can see, the cross section where you have magnetic field is much bigger than just the cross section of the core, because you have fringing magnetic field. So to make the question a little easier, they say neglect flux fringing. That said, this question is still a challenging question. There's a lot of moving parts that are happening. So let's first just write some really foundational equations that we're going to need. So the first one that I would like to write is about the MMF, and my notation might be a little bit different from the book. I basically use a capital script F to represent MMF, which is basically magnetomotive force. It's like voltage, but for magnetic field. Okay, so the magnetomotive force has three manifestations. So you can write it as number of turns times the current. You can write it as the magnetic flux times reluctance. This is very similar to Ohm's law, where flux is similar to current and reluctance is similar to resistance. Basically, reluctance is how much a material opposes the flow of magnetic field. Okay, so that's very similar to Ohm's law. And finally, the third manifestation is H times L, where H is the magnetic field intensity. Okay, it's different from flux and flux density, magnetic field intensity, and L is the mean length. So that has to do with these lengths over here, the 1 meter, 0.8 meter, so on and so forth. Those are like the mean lengths. Okay, so we're going to be using most of these equations. So a good first place to start is to take this picture and turn it into an electrical circuit. And we can actually do that because there is an analogy between magnetic fields and electric circuits. Very similar in heat transfer, how we can model heat transfer with an electric circuit. You can model basically magnetic flux and such with an electrical circuit. So basically, we have to, this is a little bit challenging because the flux is originating here, right, in the coil. So let's start there. That flux is going to go up like this, and it's going to go to this point, okay? And then at this point, the flux is going to sort of split up into two directions. Part of the flux is going to go like this. And then the other part of the flux goes like this. Okay. And forgive the fact that my lines are not perfectly lined up with the arrows here. When I scanned the book, it was not perfectly aligned. So anyway, so the flux originates here, and it splits. I call the red one, I'll call that, I guess, flux 2. So the purple one would be flux 1. Okay. So this is flux, let me use a slightly thinner marker. This is flux 1. This one would be flux 2. And then the blue is flux 3. So what happens, it's like current, basically. The current splits up, and then when it gets to this point, they add back up together to combine back into flux 1. So basically, it completes like this. And let me try to get that a little bit straighter. Ugh. Like this. Okay? So by knowing how these fluxes combine, it gives us sort of an idea of what the circuit looks like. So where the flux originates is basically like the battery of the circuit. So what I like to do is I like to first draw the outline of the circuit like this, and then I'll fill in all the other pieces in just a moment. So where the flux originates, that's going to be your, like a battery, basically. Okay. All right. And then, of course, we have one leg here, which represents this leg. I'm going to also give it a name. I'll call it leg 2. And then this one, the blue, I'm going to call it leg 3. And of course, the purple one would be leg 1. Leg 1. Okay. Now, okay, so the source is going to be your total magnetomotive force, which is sort of like the total voltage. So I'm going to write it as magnetomotive force total, right? And you can think of it like a voltage source like this. Okay. Now, here's where you have to be a little careful. So in any no material is perfect, right? There's going to be some opposition to the flow of magnetic field. That opposition to the flow of magnetic field is called reluctance. So there's going to be several sources of reluctance here. So first of all, in the region where the flux 1, the purple one, where the purple flux is flowing, in that region, there's going to be a reluctance associated with that region. Let's call that reluctance core 1. Okay. And basically this whole reluctance here can really be summarized into one resistor. We can just put it over here. Okay. So let's put that resistance here. This is reluctance core 1. And by 1, I mean the leg 1. Okay? So this represents all the reluctance in this portion. Now, in leg 2, there are actually 2 reluctances. First is the reluctance of the iron part, the iron core part itself, or steel, or whatever the material is, what they say. Steel, okay, semi-processed 26 gauge steel. All right, so it's in the steel. That's the first reluctance. Okay. So I'm gonna write that down here. That's gonna be one of the sources of reluctance. The second source of reluctance is the gap, the air gap. That's gonna be the worst, basically, because magnetic field doesn't really like to flow in air. So there will be a reluctance associated with the gap. So basically the way that you notate that in the circuit is you have one resistor here. I'll try to get that a little bit cleaner. So this resistor is the reluctance of the gap. This one is the reluctance of core 2, or you can also call it leg 2 if you'd like. So basically the current that flows in here, this current, that is the same as flux phi 2. All right. And finally, in the third leg, this whole portion is going to correspond to another reluctance. Okay. The reason that this reluctance is different from the purple path is because a different flux flows through it, so there will be a different reluctance. Okay. So let's put that here. This will be here, like this. So this is reluctance, I'll call it core 3. All right. Again, because they're different, you see the phi originates here, right? But then it splits up into two paths and then recombines over here. Okay, so it follows the movement of the flux in the circuit. So this becomes here flux, phi 3. And then the previous one was flux, let's do it in a thicker. Here is flux phi 1. Okay. Now, in the same way that we had, electric circuits, we have current and voltage, right? There's also going to be like analogy to voltage. That analogy is, as we said before, the magnetomotive force. Now, across each of these reluctances, there's going to be a different drop, drop in magnetic potential. Magnetomotive force is also called magnetic potential, just like voltage is like a potential, right? It's a form of potential energy. It just has to do with magnetic fields. So there's going to be a drop in potential energy here, and I'm going to call that F core 1. Likewise, you have one here. This will call it F gap. And this one will be F core 2. And of course, you have one more over here. This one is F core 3. And as you can probably imagine, KVL holds here. Okay, so there's going to be, right, the sum of all the magnetic potential drops and rises, the algebraic sum, is going to add up to 0 in this loop, right? Likewise, you can do the same thing in this big loop, right? Or on this loop, right? So KVL holds. And that's actually what's going to help us solve this problem. Because they give us literally just enough information to solve it. It's almost too little information, but it's actually not. It's exactly enough for what we need. So they tell us that the flux density in the gap, in other words, the flux density in the gap, is 0.2 Tesla. Now, keep in mind that flux density is not the same thing as flux. It's a little bit different. So basically, flux density, which is B, is your flux phi divided by cross-sectional area. Okay? So they are related. They're related to each other by the cross-sectional area. Now, they told us that we can neglect the fringing, which is great, because if we can neglect the fringing, that means that the cross-sectional area is the same everywhere. So that really helps us a lot. Okay? If the flux density is 0.2 Tesla in the gap and we're neglecting fringing, that means that the flux density here and here is also equal to 0.2 Tesla. So flux density is constant everywhere in leg 2, which is great. That's a great simplification that we can make. So let's add that here. So the flux density is constant everywhere in leg 2. And if you want, I could keep the color code. This is leg 2. Okay, let me just switch the scrolling to vertical because it'll help us now move. Now, this is where things might get a little weird. So flux density, in other words, B, is constant everywhere in leg 2. However, magnetic field intensity, H, is not constant. Okay, so that's something to keep in mind. If you're having trouble with that, recall that flux density B is equal to mu times H. Okay, and mu really, that's the magnetic permeability. Mu is actually mu relative times mu of air, right? So in the gap, in the air gap, right, you don't have a mu relative because it's just air. All you have is this in the gap. And that B has to be constant in the gap and also in the core. But in the core, you also have mu R, right? So the only way that's possible is if H is different. H has to be different in the core and also in the gap. It's completely different. So for example, maybe I can add like a little note here. Maybe I'll add the note here just to show you. B in the gap, it's just going to be air. So it's mu. You don't have mu relative. Mu relative is basically 1 in air. So it's just mu air times H. So this is H gap, right? And then you have B in core 2 or leg 2. That is going to have a mu relative, right? Because it's in the steel. However, in order for this and this to be equal, right, you set them equal to each other. Look what happens. Right, the mu naughts you can cancel out, right? But it's very clear that H in the gap is different than H in the core. It has to be, right? So even though the flux densities are constant, the magnetic field intensities are not constant. Okay, so that's going to be a little bit something that we need to discuss. I'm going to erase this little aside over here. So let's continue. So the chart, this graph will give us the magnetic field intensity. In other words, it'll give us H, but of course they can't make things too easy. They have to add a challenge. They don't give us H in the units that we need. They give us H in different units, so we have to convert. It's adding like a little extra step. So anyway, chart gives us magnetic field intensity in the core, but it doesn't give it in the air gap. So what we need to do now is we basically need to find H in leg 2. So from the chart, let's see what we got. All right. So again, because the flux density is constant in the gap, that means that the flux density in the core is also 0.2. So B in the core, so I guess I'll call it B2 because it's B in leg 2. Is 0.2 Tesla. Okay, that's given to us. So now we have to go into the chart and find out what that correlates to. So this chart, I did my best to, to make it legible. So first I'm going to make a line here, right? So the flux density is on this side in Tesla. I'm going to just draw a straight line like this, and then I'm going to correct it later. So I need to see where this line that I'm drawing crosses with the magnetization curve. So this curve over here. Again, when I scanned it, it's not perfect. It was a little bit off-centered. So as you can see, even though the iPad does a straight line, it doesn't completely correspond. You know what I mean? So I have to sort of compensate a little bit here. So this is a log plot. So we have to basically figure out what's going on here. So basically between 0.1, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This becomes 0.2. Okay, you count another 10, So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This becomes 0.3 here. Okay. And then over here it should be 0.4. Okay. So, and then of course here would be 0.5. And then here the resolution gets kind of difficult to see. So basically every box now would be 2. So basically it's 2, 4, 6, 8. And then this is 0.6, this is 0.7, 0.8, 0.9, and then you get 1. Okay. So we're gonna have to do our best to see where this crosses. It's like, it's kind of like, I'm getting like over here, which to me looks like 0.48. Okay, but keep in mind that, again, my figure is a little bit skewed. Okay, and actually what the book finds is actually this point over here. And maybe actually that's not that bad. It's pretty close to where it crosses. Like it's kind of hard to see, but this would be halfway, so that would be 0.45. The next one is 0.46, and where this crosses is around 0.47. Okay, so the best way to do it would be to with the textbook. If you have a copy, physical copy of the textbook, you can use a ruler and sort of draw some lines with pencil to try to see where things cross. Okay, this is the best I can do with the iPad. Okay, let me just fix this so that it looks easier to read. All right, so it's approximately 0.47. Okay, so, okay, now the units are Oersteds, okay, and we have to convert that into the usual units of magnetic field intensity, which is amp turns per meter. So the units right now of this are Oersteds, and we'll have to convert it. It's an easy conversion, just multiply by 79.577. So let's go do that down here. So 0.47 Oersteds, when we multiply by 79.577 amp turns per meter, and that this whole thing is 1 Oersted, and this is going to turn out to be 37.4 amp turns per meter. So we basically have found the magnetic field intensity in the core. Okay, so let's write that down. So from the chart, we found that the magnetic field intensity in leg 2, or core 2, I wrote it in my notes as core 2, which is basically leg 2. This is 37.4 amp turns per meter. And just to give our eyes a little, make it easier for us, let's just put this in green because we're going to need this later. Okay. Let me just give you a little heads up of what I'm trying to do. So I need to find the magnetic field intensity for this reason. Basically, what's the game plan? By now, it might be difficult to remember what they were even asking us. They want us to know, they want to find out what's the voltage, right? Now, to find the voltage, I need to know the current because they give us the resistance of the coil. So I have the resistance of the coil. If I find the current, I could do IR, get voltage. But how do I find I? The only way to find I relating magnetic field stuff is to use this formula. They give us the number of turns. So if I find total magnetomotive force, I can divide by number of turns, I get I, and then it's checkmate, I win. Okay? So basically I need to find this guy. And the only way to find this guy is essentially to find this F, this F, this F, and this F. Now how do you find those? Well, to find them, basically we remember that F gap is basically H gap times L gap. It's HL. I have it over here, HL. Right? So if I find the magnetic field intensity in the gap, and if I also find the length, the mean length of the gap, I find F gap. And I apply the same concept over here, that this is basically H core 2 times L core 2, right? We just found H core 2. What's L core 2? Just give me I'm going to erase this just so we can see, right? L core 2 is basically the mean length of core 2, which is this length plus this length. So it'd be 0.99 meters. So I take 0.99 meters, multiply by the H I just got, boom, I get F core 2. H gap, we can find it. The length or mean length of the gap is given here. Boom, I get F gap. Okay? And then from there, we basically are, it's sort of like reverse engineering the whole problem. Okay? That's basically what the goal is. So let me just, I'm going to erase because I need to have some room for later. Since this is a video, you can always go back and take a screenshot or anything like that. Okay, so we have H core 2. I mentioned this already, this next note, but it's good to mention it again. Basically, magnetic flux density is mu times H. Mu is actually mu relative times mu of the air, right? So basically you get something like this. But for the air gap, okay, B gap is actually easier because it's just going to be mu of air times H, and this is going to be H gap. So mu of air is a well-known number. It's 4 pi times 10 to the minus 7. B gap, they gave it to us as 0.2 Tesla, so we basically got it. So as a reminder, B gap is the same thing as, I think I called it B2, which is 0.2 Tesla. So H gap is basically going to be B gap over mu 0. B gap is 0.2 Tesla, and mu 0 is going to be that well-known constant, 4 pi times 10 to the minus 7. Units are Weber per amp turn meter. And this is going to turn out to be a really big number. It's 159,155 amp turn per meter. Okay. So now that we have H core 2 and H gap, I can find the voltages F gap and F core 2. Okay. So F gap is basically H gap times L gap. H gap, we just found it, was 159,155 amp turn per meter. L gap, here's a copy of the picture without any drawing on it so we can see L gap. L gap is this distance, 0.5 centimeter. So 0.5 times 10 to the minus 2 meter. Okay, so this becomes 795.775 amp turns. F core 2 is H core 2, which I have up here. So H core 2 times L core 2. So H core 2 is 37.4 amp turn per meter. L core, this should be L core 2. L core 2 is the mean length of core 2, which is basically leg 2. Okay, so the mean length of leg 2 is this distance plus this distance, which they were very kind enough to give to you. So it's 0.3 plus 0.69, so it's basically 0.99 meters. So F core 2 basically becomes 37.027 amp turns. So we got 2 of the voltages so far. We're going to get a third one real quick right now. Take a look. this whole branch, which is resistance, R gap, and R2, right? Or reluctance, rather. These guys are connected how with this reluctance? If you said parallel, you're correct, right? They share these two nodes. So this is in parallel with this, which means that this overall voltage from here to here is the same as this overall voltage. In other words, F core 3 is F gap plus F core 2. If you're not comfortable with that, do KVL in this loop and, do the whole walk around the loop, and the algebraic sum of all those voltages should be 0. And you're going to get the same thing, that F core 3 is F gap plus F core 2. So let's go ahead and do that. So that's one of the easier parts. So because F is like voltage, we can now find F3. So basically it's just the sum of these two. I'm just going to write the result, which is 832.8 amp turns. Okay, so as I'm reporting these numbers, I truncate some of them just for the sake of space. But when you're doing your calculations, a really good rule of thumb is to maintain as many decimal points as possible and only round off at the very end, at the final solution, just to avoid rounding error. Okay, so now that we have, and let me just go back here. Now that I have this, we're still several moves away from checkmate, right? We have a little bit of a challenge now, because having this number, we can't really do KVL in the big loop, and we can't really do KVL here because I have no idea what this is and I don't know what this is. So this is what we're going to do instead. From here, right, F core 3 is H core 3 times L3, right? I know what L3 is, so I can find H core 3. If I find H core 3, I can find out what is B, or in other words, the flux density in this thing, in this leg. If I find the flux density in this leg, I know the flux density here. I can add them up and I get the total flux density. By the way, I should note, I mentioned this before, but in case I didn't make it obvious, everything here has the same area. So basically, if maybe I'll do it in the same color too. If I do this, and I do this, right, it doesn't matter because they're all the same. So basically, the total B1 flux density in here is going to be equal to flux density here plus flux density here. So basically, if I can find flux density from this number, which I'm about to do, I know this flux density, I know this one, I can add them up, find this flux density. Then I find this MMF for core 1, and then boom, I'm just a couple more steps away from finishing. Okay, so let's continue. As promised, this is quite a challenging problem. It's kind of long, so let's go ahead. So now that we have F core 3, let's find H core 3, right? Because we know the mean length. So the mean length for leg 3 is basically this length. I'm sorry, from here to here, and then from here to here, and then from here to here. Luckily, they're all the same. It's just 1 meter, so it's just 3 meters. Then I can take this number, 832.8, divide by 3 meters, and then I get my H core 3, which is 277.6. Now, I could go back into the table, into that chart, and use H to find B, basically doing what we did previously in reverse. However, before I do that, I need to convert this back into Ørsteds. Okay, so that's another extra step. We take the 277.6, right? And then I divide now by the 79.577 to go back to Ørsteds. So this turns out to be something like 3.488 Ørsteds, which is very close to 3.5. So now we got to go to the chart and see what that correlates to. So let's go to the chart. Okay. So 3.5. Let me just cut this off a little bit here. So we're starting now on the x-axis. So this is 1. Let me use a different color. Perhaps I'll use, I don't know, orange, let's say. So, this is 1, and then I have 10 divisions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This division then becomes 2. Then I have here 3, and then 4, and then here becomes 5, and then again, this is now 6. This is 7. The resolution gets a little tighter over there just because they can't fit it. So that's basically what's happening here. So we need to find 3.5, which is roughly right smack in the middle here. And we have to see where that line crosses with magnetization. Do not get confused relative permeability. Please don't get confused because you're going to get the wrong answer. It's a different curve. Okay, they put them both in black and white, but just make sure that you're careful with that. So again, I'm going to draw just a rough line first. It was really far off this time, but I'll fix it. And we're going to see where it crosses. So it crosses roughly here. Okay, so now we have to see. Again, I'm going to draw the line. Oops, I'm going to draw the line. And then I will correct it. Like here, roughly. Maybe a little bit high. It's maybe a little bit higher. I don't know. From this distance, it looks pretty good. Now it looks too high. Whatever. I mean, you get the idea. It's just slightly above the first tick, above 0.4. Let me get it. There. That's good enough. Okay. So notice between 1.4 and 1.6, there's 1, 2, 3, 4, 5 divisions. So you're basically taking a distance of 0.2 and cutting it in 5. You're dividing it in 5 sections. So basically this is, if you do the math, you'll see that this is 1.44. Okay, this is 1. You add another, so 1. So again, 1.4. So let's do it. 0.2, and then we divide by 5. So this should be, let me grab the calculator to make sure I got this. So 0.2 divided by 5 becomes 0.04. So it's always 0.04. Okay. So this the first tick is 1.44. This becomes 1.48, 1.52, right? So on and so forth until you eventually get to 1.6. Okay. So this is 1.44. This one would be 1.48. So basically the line is somewhere in between 1.44 and 1.48. It's a little bit closer to 1.44. It's not quite smack in the middle. So it's roughly around 1.45. Like so. Okay. So it's about 1.45 Tesla. Maybe I should put the units. That would be smart. Okay. 1.45 Tesla. So that's what corresponds to that magnetic field intensity. So maybe I should put, this is the Ørsted's, approximately 3.5 Ørsted's. Okay. It corresponds to 1.45 Tesla. Okay. So now let's go. So this is approximately 1.45 Tesla. Okay. So I mentioned this earlier, but it's good to mention it again. Because everything has the same cross-sectional areas, we can just add the B's instead of just adding the fluxes. The solution in the textbook, they convert everything back to flux, but you don't really have to because everything has the same cross-sectional area. You're going to get the same answer. Why is that? So I'll write it again. Remember, B is flux divided by unit area. So basically, you know, we have that flux 1 breaks up into flux 2 and flux 3. But because everything has the same area, if I divide all the parts by area like this, right, this becomes B1, or the total flux. This would be B2, and then this would be B3. Okay, that should be a 3 there. And I can keep the color code if you'd like. This is, you know, red. This one is blue. And then this is purple. But the area, I leave it the same color because it's the same area. So what's flux B2? It's 0.2 Tesla. What's B3 is, we just found it, 1.45 Tesla. So B1 now becomes 1.65 Tesla. Okay, so basically now we found B in here, which is like sort of like the current, but it's not really the current. It's like the current density, I guess you can call it. But it's like the current in here. So once I have that B, right, now I can go here and well, I take the B, I go here to find magnetic field intensity, go back here and calculate F, and then I can do KVL, get this F, and then finish off the problem. So let's go ahead and do that. So we need to find H core 1 from the graph, and this should not be in orange because I reserved orange for the magnetomotive force. This should be like just like this. So let's go. So we have B is 1.65. Okay. So I'm going to use another color. I don't know, purple maybe. So this is 1.6. This becomes 1.64. Then this becomes 1.68. Right? So 1.65 is like maybe just slightly above the first tick above 1.6. So let's draw the line, and then I'll correct it. So I'm going to try to, I kind of got it right on the dot, but hold on a second. I need to make it longer so that it reaches the magnetization curve. Come on. This is not cooperating with me. Okay. All right, so it reached the magnetization curve. Now we have to zero it in. So it's just above the first, you know, something like that maybe, or like this. I'm trying to mimic what I have down here because it's around the same value. So this is 1.65. Oh boy, where does that cross? So that crosses, and my resolution is, it's not bad, but it could be better. It crosses around like here. Something like that. So let's see what that is. Again, I'm going to draw the line. Oops. I'll draw the line and lock it in. Hold on a second. It's like somewhere there. So I wrote some of these numbers before. So this is 10, and this is 20, this is 30. So this over here is like 40. So I'm getting approximately 37 Oersteds, which is, I believe, exactly what they got. Let me just double check. Yes, they got approximately also the same thing. 37 Oersteds. Okay, so we did a good job lining things up here. All right, 37 Oersteds. And then we got to convert that to H. Okay. So we need to find H core from the graph. Again, we used B1 was 1.65 Tesla. From the graph, we found that H core is approximately 37 Oersteds. Okay, and then we have to convert it by multiplying by 79.577 amp turn, amp turn per meter. That should be a turn. It's going to bother me. Amp turn per meter. And that's like 1 Oersted, right? So the units all cancel. I know sometimes I do it in script, sometimes I do it in print. I should be more consistent. Okay, so we multiply that out, and we find that H in that leg is 2944.35 amp turn per meter. So now we're almost there. We can almost taste the victory. We have to now find F core for F core 1. F core 1 is basically H core 1 times L core 1. H core 1, we just got it, 2944.35 amp turn per meter. L core 1 is here. It's basically this distance plus this distance plus this distance. So it's basically 0.8 plus 0.8 plus 1. So 1 plus 1.6 becomes 2.6. 2.6 meter. And this becomes 7655.31 amp turns. And now we can use KVL to get F total. So let me just use the circuit we had. I'm going to grab this circuit using the beauty of copy and paste. Okay. And basically we're going to write KVL in this loop. Now you could also, by the way, you could also have written KVL here. It's the same thing. It's really, you're going to get the same answer. Excuse me. So KVL states algebraic sum of all the voltages in that closed loop should be 0. All right. I'll start at this corner and then work my way around. So basically you get, minus FT plus F core 1 plus, then you're going to have, F gap plus F core 2. And note, of course, that this is the same thing as F core 3. Let me try to keep the color code. All right. And then we're going to get F total. So basically, F total is going to turn out to be F core 1, which was the 7655.31 amp turn. I'm just going to write down the F3, which is F core 3, which is the same thing. 833.59 amp turns. And this turns out to be 8488.9 amp turns. So now we're literally just 2 steps away from checkmate. FT is what? It's NI. Now they don't want I, right? They want voltage. So we can use Ohm's law. What's I? It's just V over R. And now we can just solve for V. So solving for V, right, it's going to be F total times R divided by N. So plug and chug, and that's checkmate. We got it. resistance they gave you is 0.05 ohms. The number of turns is 80 turns, and you should get 5.3 volts. Okay, that is the entirety of part A. Success. Now, there is a part B, and actually part B is really easy because we did all the heavy lifting in part A. So we'll take a look at part B real quick, just finish it off. This is using equations 1517, determine relative permeability of each of the three legs. So they want the relative permeability of each leg. And it's not too difficult to do because we remember that B, right, is mu relative times mu air times H. So if I rearrange this, I can find mu relative is what? It's basically B over mu naught H. We have B in all the legs, we have H for all the legs, and mu naught is a constant, so the rest of it is just plug and chug. Of course, you could, so let's do it plug and chug, and then I'll show you the other way. The plug and chug is the easier of the two methods. So for leg 1, what was B1? B1 is 1.65. That's B1. So we have here 1.65. Mu naught is a constant. It's 4. That should be a 4. 4 pi times 10 to the minus 7 Weber per amp turn meter. And then H would be H core 1. So H in leg 1 or core 1. I know we did it. I just have to find. Here it is. 2944.35 amp turn per meter. Okay, by the way, this is Tesla. $29.44.35 amp turn per meter. Okay, and this overall will be 445.95. Okay. Unitless. Okay, the amp turns cancel. Whoops, right? Amp turns cancel amp turns. Meters become meters squared. Weber per meter squared is Tesla. So basically, the Teslas cancel, and you just get unitless. Okay. For leg 2, it's the same thing, but just the numbers are going to be different. So I will use the beauty of copy and paste here. Leg 2, B was not 1.65. This is the one they gave us. This one was the 0.2 Tesla. The mu naught is still the same. H is different. Now, be careful, because in leg 2, right, they want us to find the relative permeability of the core, right? Not of the gap. The permeability of the gap is easy. It's just mu naught. We don't have to calculate that. So we need H core, not H gap. So H core 2, we did it here. Here it is, H core 2. So this is the H magnetic field intensity only in the core of leg 2, in the steel. So we put here 37.4. And this should turn out, my stylus didn't, okay, should be 4255.34. And finally, in the last leg, again, we just have to change the two numbers. We just change this guy and this guy. In leg 3, it's the Tesla, the B3 is 1.45. And then H core 3 was 277.6. Let's just verify that. H here. Okay. This is, in case you're watching this, this is for Ørsteds. Maybe I should have put the units there. Ørsteds. Okay. So, all right. And this becomes 4156.69. And that's basically it. That's how you solve this problem. I find this for part B to be the easiest way. If you want to do it the graphical way, you could do it the graphical way. I mean, the math is not that difficult, but if you prefer to do the graphical way, you just take the H for all the legs, convert it to Ørsteds, and then once you have the Ørsteds for all the legs, right, you're gonna find out where the Ørsteds now cross with the other curve, which is the relative permeability curve. You should get roughly the same values. Where are you going to read the y values? So like, let's say you're over here, you got to read them on this side, relative permeability. Okay. As I said, I much prefer to do it with calculations, just because this graph, you know, it's kind of has very thin lines and stuff. So I find it easier to do it the other way, but it's up to you. And that's how you solve this problem.